Hey folks, welcome back. This time around it's modal transient dynamic analysis. So just to give you an intro, we did frequency analysis first, we did transient direct formulation analysis, and now we are doing modal analysis transient. So whatever, you have that brackets from last video. Same thing, but this time not direct transient, but modal transient. And you might be wondering, well, what's the difference? You did not really talk about what's the advantages and what's the disadvantages. Could you elaborate that a little bit, young folk kid? Yeah. So sure I can, because I can Google. Now, really, I found that page to be really helpful. So you have direct, and it's not the same page than this, but both are helpful, to be fair. So yeah, I quit the nonsense talk here and go into the topic. Now you have direct transient response analysis. So you know what it is. It is imaginary algebra, complex algebra, using to directly solve the issue. In this case, a transient problem. It's not really a sub problem. A transient problem, and it's a direct solving of this problem. So it says that it's more efficient when you use high frequency excitation because, again, the other one, modal transient response analysis, will require to extract the modes. If you have a huge frequency, you would have to extract a lot of modes until there. So better use direct transient response analysis there. But from another point of view, the modal transient response analysis, rather than using the physical approach and the physical degrees of freedom, it uses the modal degrees of freedom, which can be, or usually are, less than the physical degrees of freedom. And that means that you have a faster solution. So it can really impact your running time. And so, yeah, so those are the two balances here. So can significantly impact the runtime. Yeah, I talked about that. Big saver for transient models with large number of time steps. Yeah, we won't have that here. We have just one time step, but yeah. No, not just one time step. It's a multiple 800, but it's rather small. Okay, now let's jump into it, I guess. And the tutorial I will be following today, as you have already guessed it, it's the modal transient dynamic analysis of the bracket. Now, let me begin here, and just to point things out first again, and I will do that in a shorter version than with the other video. If you want to have the longer version of that explanation, go to the direct transient, because it's the same thing. You have to change two things here, at least of now, December 2022, in order to be runnable with Hyperworks. And we do that here. First thing, you have sets, and one of the sets is later required to have a global output request referring to that set, and for that you should apply a card image. And so I will do that here, card image set 1. I will have to apply the node again. It's the sender node here. Yeah, so this is it. First problem. Second problem is the solver mass. Delete it. Go to no ribbons for me. And that was wrong. No panels for me. Ribbons are good. Now, it's in model ribbon, and then you find, yeah, masses. And then you are in the panel area again. I will move myself up a little. And you would want to just select the node here and put in a number of 1,000 units. I don't know what the units are. And conm2 is the right property. It's not a property, it's a element type. And just hit create. You create a mass here, and the solver mass doesn't work. That's it. Now we can start with the tutorial itself. So what we have here is the bracket again, and the bracket is fixed here. You can see this with the SPCs. SPC load collector is already set, and we have a mass here, which we just created. And yeah, we will apply a load here on this bracket area. Somehow I thought of it to be a chair. all time, but it's not. It's a bracket. Yeah, whatever. You will apply a force here, pushing it down, and you would want to see what this is doing, how this is balancing, right? This is more or less it. And the direct analysis yielded that result pretty quickly, and so will the modal analysis as well. First off, we want to create our curve again. Which curve? Which curve? The curve of how your force is time dependent, because we are doing a transient. That means we're stepping in time. Time has a meaning. Or is that right? I'm always confused about it. But dynamic means more or less the same thing. Time has a meaning, a physical meaning, not just a incremental meaning for applying a load with a time step, and you can see you can say halves of the time step is half of the force or so. No, it's not that. Here it's really seconds. And you will have to apply 1500 units, but in this manner. So you have 0 units until 0.1 seconds. And then you're stepping up your game here to 1500 units. And this is your curve, which we want to create at first here. So right click, create a curve. And once again, I will have to, yeah, it's so huge, but yeah, that's because of my screen. It spans over. It's killing me. But let's just go for it now. Table D1, because I think you can see everything either way. So yeah, I will do it just for the sake of speed. 0.1, 1. Is it 1? Is it 1? Let me see. Yeah, and it is 0 here, but it is 1 there. So this should be it. And now I will just decrease the size that you can see it. Now you see that's the curve we created, same thing as the thing here. And yeah, that's just stepping up the time. So you might be wondering, well, didn't you say 1500 units? Why is it 1 here? Because you will include the 1500 as an amplitude in the constraint, which we're creating in a minute. So this is the reason. All right, and then do not forget, please, 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 do not forget to change the curve to be table D1, because this is usually a tab DMP1 card, and this is not what we want. We want a table D. Table D1. Okay, so why is it disappearing? Because you're in the curves tab DMP1 collector browser, and this is not existing anymore, so that's the reason why you don't see it. But here within the model browser you can see it in table D1. Yeah, so this is fine. Now we have that, and I'm just, yeah, we will create it. We will create another curve later. I was just confused because I want, yeah, there will be another curve later. And yeah, so next thing, T-step. Time step, load collector. Yeah, this is a load collector, not a load step input. And we call it T-step. And the card image should be T-step. All right, number of time steps is 800. Time step interval is 0.005. Yes, so 800 times 0.005 yield in 4 seconds. And this NO is set to 1 to not skip anything. We want to have the complete output. Next thing, we create a load step input. In this case, it's it's a load collector again. And this is the load collector which is used for the constraints. So this will actually use create the time-dependent load. This is where I said that the 1500 as an amplitude will be set into here. So no card image, just the name, and load collector has now the area, right? I will move up myself a little to not hide the view you will see right now. because we now create the constraints. So this is done in analyze ribbon, then you have BCs, and then you have constraints. And here we will use again the set force to choose our nodes. It's also possible to create a set here, to assign a set here, but be careful. This is not possible, I think, for the load type the area. You see, the area, you change that to the area, which you are required to do. Better do that at first, because, yeah. I have done that multiple times that I created SPC, but I wanted at the area. So, yeah, better change that first, then go on to your DOFs, and then go on to your node selection. So that's just my suggestion. So nodes, you can just choose by sets. That will just bring you up that little selector again. Now, force is the set we want to select, so select it here. And you can see the orange nodes here, which are selected. And it is already set to the right thing, so DOF3 is selected, and you see the -500, it's exactly there. So -500 as an amplitude, you could say, or a multiplier for the curve is being done here. So create, you can see it. If you want to validate that they are really there, you can also make it transparent. You can see that. And yes, that's all fine. Now, next step is to create another curve. And this curve is because the damping, you have now a frequency range, and you would want to create a condition that you have a damping dependent on the frequency. Because later on, you're just playing around with mode shapes, and you want to have the structure, the damping, the damping to be, resolvable. And so you have to give it in sort of a frequency dependent form. So it's a modal damping table you create here. And this is done the same thing as before, create curve here. Again, our beautiful big curve editor. We'll just shrink it down here and rename that to, how should we rename that here? Tab DMP. Yeah, DMP1. So we just see what it is. So, and we want to just give two values. First one is 0, and the y-axis should be 0.02, which is our damping. If you remember that from the last tutorial, it's the same value for the structural damping we used. So 0.02. So this is the damping. So basically what's that's doing, it's populating here the frequency and damping values to have from 0 to 1000 Hertz, you have the damping to be 0.02. That's it. All right, then for the modal analysis, we would want to have another load step input because, it's the ideal value, because you want to specify the range where to extract modes. This gets me always confused. You have to pay attention to that. You have to double tap on tab. 1, 2, then you're in the next one. It's a little bit, I don't know. Maybe there's a reason behind it. But yeah, you create a load collector or load step input in that case called IGL. And this just specifies 0 to 1000 as a range for mode extraction. Yeah, that's it. And then you would create another load step input. And this is because we have not tied together our constraint with the amplitude of -1500 and the actual table D1 curve. So this should be done too. And this is the thing here with dynamic load time dependent. Now, it's pretty straightforward. So you have excited. Now, which load collector should you excite? For sure, the D area. And then you have the table D. You would suggest to have the table D1 card. See that it also hides your tab DMP1 card. That's because the tab DMP1 table or curve is used for damping. You can also look that up in the help. You can see that here. Defines modal damping as tabular function of natural frequency. Right? So you have that in the card image. And that's why it's not showing here, although being a curve. So you select that, and this is selected. I just make sure that it's load here. I don't know why. I don't trust it. I'm not sure why. I had a problem at the beginning with the model and didn't run, but yeah. I really don't think it's that, but yeah. So I just be sure that it's type load. And then I think that's it for this thing. Then we can go ahead and create the load step. Maybe I will just create a better name for here that I can find with the load step better, because that I did wrong with the last video. Yeah. So I want to create a load step. Right click, create load step. Where is it? Load step. Now, what should it be? The analyzer's type here should be a transient. In this case, modal, not direct. And now just comes the happy assigning again. So SPC would be SPC. That's easy. Deload is also straightforward because the dynamic load would be the time dependent T, the time T-load. And now I think the eigen would be the method struct, if I'm not mistaken. And we have a T-step, be aware that there's a time. So yeah, choose time. And I think that's it. Let me see. SPC is set, deload is set, T-step is set, method struct is eigen. And oh no, we forgot the curve for the damping. So as damping struct should be assigned as well. So all right, now we have that. And we can go ahead creating output requests. And yeah, I mean, by now you know all the drill, so I will not talk too much about it. So we go in here and go to next and global output request, check the displacement collector, and go for form both, and go for right, go for option to be a set ID, which just defines, I just don't want all nodes to be in my output request, but just some. And those nodes should be in a set, and this is the center set, which is one node, and that's fine for me, right? This is it. So nothing special here. Going on, we have the displacement output request, and then we just want to, because there's no damping set, no viscous damping factor with the direct method. You had all those kind of stuff you had to do. So it's just this one and the output. No param card. Param. No, just output. And this is the same thing again. So we want to have two outputs. And the one output should be the normal standard H3D. And we want to have all. And the second output is again the HG trans, which is hypergraph transient data. And also all here. Return. Now I think we are done with setting up the model. So we can save it. File save as model. I will just create another file to be with a 2 that I have no name collision, because I did that tutorial a few times and made sure that I understand it correctly. Now analyze OptiStruct and go for it. Hopefully I did not make any mistakes. That would be a pity, because then I would have to search for it. But it seems like it's running. Now, yep, that's about it. We can click on results, and yeah, I will show it this time the other way around. So this is more or less the output you get, and here you can also just animate what the thing is doing. So just hit on a contour, hit apply, and also go with the scaling, maybe to, let's go crazy on that one, make 1000, and then just hit the play button. Yeah, I see it's bouncing around. Yeah, so this is one thing of an output you can get. So this is the real-time thing. And it's also good to check that for if it's reasonable what it's doing here. The other one is you can open a session. And this is called with your name and then underscore, I think Tren, I'm not sure, but you will see in a minute. Yeah, so this is with underscore Tran at the end. Now that's your displacement output, and I don't know, but something about it is just oddly satisfying. Because I had that model running without any damping, and it did not run. Not the modal one, but the direct one. And I was going through the roof about it because I could not get that thing to be like it should. But yeah, so it's satisfying to me to see it that it's what it's supposed to be, right? And it's just a nice output. So if you just want to have the curve of interest because X and Y is not really that interesting, you can just turn that off again, like in the last video, and then just fit the curve again. And so you have it ready for your output wherever you want to do that. Screenshot, put it into a Word or a PDF file, and you're good to go. So yeah, that's about it. I mean, it's pretty interesting that it is. If you have done it a few times, it's really rather easy to put it up. And yeah, I would encourage you to just try it a little bit. And yeah, if you want to have anything special going beyond this kind of transient dynamic analyzers, one thing on my list for sure is the random the response on a random excitation function. Also, my German kicking in. So this is a random response analysis. I think this is what I will do next. I'm not really sure if yeah, I think this is what I'm doing next, because that was also a request by you guys. But if you have anything further or anything different on that, or a problem maybe, just leave a comment, write me a mail or so. And if you like the video, please like, subscribe, hit the bell, you know what to do. Thanks for watching, thanks for being around, I really appreciate it. And yeah, see you in the next video. Bye guys!